single crystalline iron silicate.
Good afternoon, everyone. My name is Hsiu-Ming, and I'm a master's student of Department of Material Science Engineering at National Tsinghua University in Taiwan. And the topic of my presentation today is growth and characterization of single crystalline iron monosilicide and beta iron disilicide nanomers. My presentation is in 4 parts: introduction, experimental, results and discussion, and conclusions. By the end of this talk, you figure out the main factors and mechanism in nanowire synthesis using CVD, chemical vapor deposition method. One-dimensional nanostructures are promising for bottom-up microelectronics because of their novel properties such as electrical properties, low defect density, and high compatibility. And in this work, we demonstrate the rapid growth and structural characterization of single crystalline iron monosilicide and beta iron disilicide nanowires by a spontaneous CVD method. Why does iron silicide has attracted so much attention? Iron monosilicide is a narrow bandgap semiconductor with a cubic structure and has been classified as a conduit insulator. And beta iron disilicide has a direct bandgap, which makes it a promising choice in infrared detectors and light emitters for silicon-based optoelectronics. Let's move on to our experiment. Figure 1 is the schematic illustration of our experimental procedures. It was carried out in a 3-zone furnace tube, and the substrate was silicon 100, and the substrates were cleaned in acetone, isopropyl alcohol, and dilute hydrofluoric acid. And these substrates were put into crucible A, B, and C. The precursor was iron chloride powders, and it was put in an aluminum boat at the upstream here. And the carrier gas was argon, and the flowing direction was like leaks from upstream to downstream. And in order to figure out the factors that influence the results of our experiment, several processing parameters such as temperature, ambient pressure, and gas flow rate were varied studied. TEN, SEN, TEN, XRD, and EX were utilized in our analysis and characterization. SEN images show the morphology of our parts. Figure A was the case of 650 degrees Celsius, and we can find no nanowires but thin film on substrate. And in figure B, in the case of 750 degrees Celsius, the products were short in length, and the diameters was about 70 to 100 nanometers. It was difficult for us to call them wires. And when we raised the temperature to 850 degrees Celsius, the results as figure 2C. And products with the highest aspect ratio, and now the diameters was about 20 to 40 nanometers. Now we can call them wires. When we raised the temperature to 1000 degrees Celsius, figure 2D, and we found thin film on substrates again, but with coarse grains. At high temperature, it was easy for our precursor iron chloride to transform into vapor phase and be transported to the substrates, and which increased the reaction concentration in the closed tube fast. And so the reaction concentration in the furnace the reaction rate in the furnace was really fast, which makes the morphology of our products from nanowires to thin film. And at 650 degrees Celsius, the temperature was not high enough, and it was difficult for iron chloride to transform into vapor phase. And so the reaction rate was slow, and 2 hours was not enough for it to grow nanowires. Comparing these two pictures, figure D and E, you case of the case of products grown at 1,000 degrees Celsius for 2 hours and for 5 minutes. And we can see that the reaction rate at 1,000 degrees Celsius was pretty fast, and several minutes was sufficient and suitable for them to grow nanowires. Other than temperatures, we are also interested in the effects of ambient pressures. And here is the pictures of products grown at 0.3 torr and 2 torr, 50 torr, and 100 torr. And we found that the diameters of the products increased along with the increase of ambient pressure. And the phenomena may be explained by an empirical formula we propose. It is under Adobe Math, and equation 1 indicates that the ambient pressure in the furnace tube was determined by partial pressure of argon and iron chloride. And when we raise ambient pressure, we raise the quantity of argon. By raising the quantity of argon, we increase the ambient pressure, and which makes the concentration of iron chloride decreased. And equation 2 indicates that the free energy for nucleation is a function of reaction concentration, C. And equation 3 indicates that the critical size of nuclei is a function of free energy for nucleation. And we can find that as the reaction concentration decreased, we decrease the free energy for nucleation, and which increased the critical size of nuclei. And large nuclei would increase the diameters of nanowires at the end because of atomic diffusion. And this explains why nanowires grown at higher ambient pressures possess wider diameters. We have just discussed the morphology of our products, so the next question is to identify their chemical identities. Figure 4 is the XRD spectrum of our products grown at different temperatures. Green, and blue, red, and black lines represents 100 degrees Celsius, 850, 750, and 650 degrees Celsius respectively. The blue points and yellow points out the characteristics of iron monosilicide and beta iron disilicide respectively. And from this picture, we can see that at 1,000 degrees Celsius, the phase of the products was iron monosilicide, while at 850, 750, and 650 degrees Celsius, the phase was beta iron disilicide. The next picture is products grown at different ambient pressure. That's also green, blue, red, and black line represents 0.3 to 50 and 100 torr. And let's focus on the peaks in this red circle. The blue points point out characteristic of iron monosilicide, and the red one represents beta iron disilicide. And we can see that the peak of iron monosilicide, 211, was decreasing along with increase of the ambient pressure, which indicates that the content of iron monosilicide decreased at higher pressure. Here's our TEN analysis. Figure 5A and B are TEN image, HRTEN image, and corresponding diffraction patterns of iron monosilicide nanowires grown at 1,000 degrees Celsius for 5 minutes, which share the same experimental condition with our previous figure 2E. From the HRTEN image, the growth direction was 111, and the interplanar spacing was 0.259 nanometers, and the diffraction pattern with long axis of 1, 2 bar 1 indicates that the structure was single cubic. Next page is the PE and HRT and corresponding diffraction patterns of beta iron disilicide nanowires from at 850 degrees Celsius for 2 hours, which share the same experimental condition with previous figure 2 seen. From the HRT image, the growth direction was 202, and the interplanar spacing was 0.367 nanometers, and the diffraction pattern with zone axis 1 bar 1 1 indicates that the structure of which was orthorhombic. And as you can see from these pictures, the nanowires were all single crystalline. Okay, we have just discussed the morphology and chemical identities of our products, and we propose that the morphology and the phase field form is associated with the reaction concentration in the furnace. So in order to verify the thought, a method was utilized here, and we conducted the experiment again, but the silicon 100 substrates were replaced by alumina substrates. And these alumina substrates were taken to element analysis with EDX. And figure 6 show the results. Figure 6A was the ADX analysis for products grown at 650 degrees Celsius, and B 850 degrees Celsius, C 1000 degrees Celsius. And in this picture, the y-axis represents the position in the furnace, A, B, and C. It was near to farther from the cursor. And the y-axis represents the percentage of iron. And we can see, let's focus on the y-axis. And at 650 degrees Celsius, the maximum was about 5%. As 850 degrees Celsius, the maximum was about 6.5%. And at 1000 degrees Celsius, it was more than 16%. Obviously, the reaction concentration in the furnace increased along with increase of temperature. And as we consider the gas flow rate, black, red, blue, and green lines represents 10, 20, 100, and 200 SCCM. And as you can see, when we raise the gas flow rate, the concentration distribution in the quantity was more uniform. And as we consider the deposited positions, when the gas flow were lower, and reaction concentration at position C was higher than that at position A and B. This was due to the fact that in our experiment, the pump was put at the upstream and consistently put out the gas. So makes the probability for precursor to deposit on position C increase. And so the last question is how the nanowires grew. At low supersaturation, which the reaction concentration was low, beta iron disilicide was formed at high supersaturation, and iron monosilicide was formed. There were several steps in the growth process of nanowires. First, macromolecules nucleate and deposit on the substrates as particles. And second, these particles migrate and agglomerate on the substrates to form thin film. Then nanowires grow at heterogeneous nucleation sites on the thin film. And in our experiment, there were no catalytic metal droplets found on the tip of the nanowires, which suggested that the growth mechanism of the products in our experiment was not built as vapor-liquid-solid mechanism, and we propose that it might be as vapor-solid mechanism. in conclusion, we have synthesized single crystalline beta iron disilicide, iron monosilicide beta iron disilicide nanowires, and especially beta iron disilicide nanowires. It has been wanted but seldom accomplished with CVD method. Processing parameters such as temperature, ambient pressure, and gas flow rate were investigated. Preliminary physical characterization with XRD and TM verified their chemical identity, and we also proposed growth mechanism. We appreciate the support from Ministry of Science and Technology and National Chengtong University, and this is my first time to be in a conference like this, and this is my first time to be in Europe. I want to thank my advisor,呂國彰, and my trip partners. I want to tell you, I love Europe, I love friends, I love beer, and thank you very much.